Welcome to a presentation on no reference opinion unaware quality assessment of authentically distorted images. I am Nithin, and this work has been done with my colleague Vignesh under the supervision of Professor Rajiv Soundararajan in the Indian Institute of Science, Bangalore. Image quality assessment, or IQA, refers to the analysis of perceptual quality of an image that gets affected by distortions. For example, synthetic distortions like synthetically added blur, noise, or compression artifacts, or authentic distortions that are baked into a camera captured image like object motion blur, overexposure, lens artifacts, or a mix of multiple distortions. In no reference or blind IQA, most of the popular methods use a dataset of distorted images and their corresponding human opinion scores on the perceptual quality to train a quality assessment model. However, obtaining human opinion scores is a highly resource consuming task. This motivates the need for completely blind IQA, where we take away this need of human opinion scores. In our work, we focus on deep feature learning for completely blind IQA on authentically distorted images. In the next couple of slides, we'll describe our main method. We start by pre-training a network on the M-scale framework that performs contrastive learning on synthetically distorted images. In contrastive learning, there is this notion of anchor, positives, and negatives, where the positive features are pulled closer towards the anchor, while the negative features are pushed farther apart. In quality feature learning, the negatives are differently distorted versions of the same scene. Now, when we think about representation learning on authentically distorted images, we do not have negatives. This motivates us to use the SimSciAM framework, which only uses positives. Here, we take two large crops from an authentically distorted image, which represents the global quality of the entire image. These patches are passed through the SimSciAM framework on the right to compute a dissimilarity loss. Although this learns the quality representation of the entire image, it can also learn the content correlations between two of these patches. This motivates the need to reduce content dependence, which is achieved by minimizing the mutual information between the learned quality features and the content information. Here we use the contrastive log ratio upper bound on the mutual information between the content information Y and quality information Z. The content information is extracted using a pre-trained ResNet trained on classification passed through a softmax layer. In this expression, the conditional distribution of content information Y given the quality information Z is not known. Hence, we estimate it using a variational approximation network Q theta. The loss term here is added with the dissimilarity loss discussed earlier to learn the feature encoder with reduced content dependence. Now, to predict the quality score, we pass multiple patches of the input image through our learned feature encoder to fit a multivariate Gaussian model on the features. The same procedure is applied on a corpus of pristine image patches. Finally, to predict the quality score, we compute the distance between these distributions. Comparing the performances, we see that our proposed method outperforms all the other completely blind IQA methods on most of the datasets. Concluding our talk, we have explored completely blind IQA with deep features on authentically distorted images. We observe the need to mitigate content dependence in unsupervised quality feature learning, especially in the case where we do not have negatives. Finally, the design of such completely blind IQA methods is promising and more generalizable. With newer distortions emerging from evolving camera sensors and algorithms, one can improve or scale the method without the need of human opinion scores. Thank you. The code and pre-trained models of our work are publicly available in the link below.